Most technological revolutions don't arrive with announcements. They arrive quietly. The transition from horse-drawn carriages to automobiles didn't happen overnight. Neither did the shift from landlines to mobile phones or from film to digital photography. Energy storage is now approaching a similar moment. Not a sudden replacement, but a tipping point. And according to engineers, manufacturers, and regulators,
for most of the 20th century,
power flowed in one direction.
From centralized
passive
consumers. Power flowed in one. That model no longer holds.
Today, batteries support everything from electric vehicles and Today,
they stabilize power grid. They store intermittent solar
and increasingly, they act as silent insurance policies during outages.
As our dependence on
stored energy
limitations of existing battery technology become more visible. Most technological revolutions don't arrive with announcements. They arrive quietly. The transition from horse-drawn carriages to automobiles didn't happen overnight. Neither did the shift from landlines to mobile phones or from film to digital photography. Energy storage is now approaching a similar moment. Not a sudden replacement, but a tipping point. And according to engineers, manufacturers, and regulators, that moment is approaching around 2026. Lithium-ion batteries rose to dominance in the 1990s because they solved a critical problem: energy density. Compared to older chemistries like nickel-cadmium, lithium-ion batteries stored more power in less space and weight. Their basic structure is elegant. Lithium ions move through a liquid electrolyte between two electrodes, releasing energy in the process. But this design also introduces constraints. Liquid electrolytes are chemically volatile. They degrade over time. And under extreme heat, physical damage, or manufacturing defects, they can fail catastrophically. The industry has spent decades mitigating these risks through cooling systems, protective casings, and software controls. Those solutions work, but they add complexity, cost, and physical limits. Lithium-ion technology has now reached a point of diminishing returns. Each new generation brings modest gains, slightly better efficiency, slightly improved safety, but not a fundamental leap forward. At the same time, the demands placed on batteries are increasing rapidly. Electric vehicles require faster charging and longer ranges. Grid-scale storage requires longer lifespans and higher safety margins. Home backup systems must operate reliably indoors, often unattended. These growing demands are pushing engineers to look beyond incremental improvements toward structural change. That change arrives in the form of solid-state batteries. Solid-state batteries replace the liquid electrolyte with a solid material. This may sound like a small adjustment, but its implications are significant. Without liquid electrolytes, the risk of thermal runaway is dramatically reduced. Solid electrolytes are far more stable under physical stress and temperature extremes. This stability allows for higher energy density, meaning more power stored in the same physical space. It also allows batteries to last longer, losing less capacity over thousands of charge cycles. Just as importantly, solid-state batteries perform more consistently in both hot and cold environments. That reliability is essential for electric vehicles, outdoor infrastructure, and residential energy systems. Given these advantages, it's reasonable to ask why solid-state batteries haven't already replaced lithium-ion. The answer lies in manufacturing. Solid electrolytes are difficult to produce at scale. They require extreme precision, uniformity, and near-zero defect rates. For many years, production yields were too low and costs too high for commercial deployment. But manufacturing techniques have matured. New materials have proven more stable, and large-scale pilot production lines are now demonstrating consistent results beyond laboratory settings. This is why 2026 matters. Industry roadmaps increasingly converge on the mid-2020s as the point when solid-state batteries move from demonstration to deployment. By 2026, automotive manufacturers expect limited commercial rollouts. Energy storage companies anticipate grid-scale trials. Regulatory bodies are increasingly favoring non-flammable battery chemistries in safety-critical applications. This does not mean lithium-ion batteries will disappear. Instead, it marks the beginning of a layered transition. Solid-state batteries will first appear in applications where safety, longevity, and performance matter most. For homeowners, this transition is already underway in quieter ways. While solid-state systems may define the next decade, today's most advanced lithium-ion systems already reflect many of the same design philosophies. Modern portable power stations now include intelligent battery management systems, thermal monitoring, modular cell design, and software-based safety cutoffs. These systems are quieter and cleaner than traditional fuel generators. They require no combustion, produce no fumes, and are safe for indoor use. As battery technology evolves, many people choose to bridge the gap between today's electrical grid and tomorrow's energy systems with portable home backup solutions. High-end systems from companies like EcoFlow and Jackery use advanced lithium-ion cells paired with sophisticated safety controls. They embody many of the priorities driving the transition towards solid-state technology: longer lifespan, improved safety, and intelligent power management. They are not replacements for future battery systems. They are transitional layers in an evolving energy ecosystem. The most important technologies rarely announce themselves. They earn trust gradually, through reliability, safety, and quiet presence. Solid-state batteries may define the next era of energy storage, but the transition has already begun, one system at a time.